we are going to start a new section on closed sets and limit points. Let's start with the definition of a closed set. Let x comma tau be a topological space and let A be a subset of X. We say that A is closed in X, or simply that A is closed if the complement of A in X, that is X difference A, belongs to tau. This just means that A is closed if its complement is open. Example 1. Let's consider the set of real numbers with the usual topology, and let A and B be two real numbers such that A is less than B. Then this closed interval is closed in R according to that definition, because its complement in R is this union, the union of these two rays. And rays we already know are open in R in the usual topology. Why? That is because rays form a subbasis for the topology on R, the usual topology. So this is open in R, this is also open in R, so their union is also open in R. So that is why by definition this interval is closed. And this is the reason for calling this type of intervals closed intervals. Next, example 2. In this one we consider the plane, the two-dimensional plane R2 with the usual topology, and our set A is this set. It consists of all points, both of whose coordinates are non-negative real numbers. Geometrically, this is the region that A represents. That is the first quadrant along with this axis and this axis. Only the positive part. Of course, the origin is also present. So these boundaries are there and the first quadrant is there, that is A. And this is closed because the complement of A in R2 is this union. Do you see what region this represents? Minus infinity comma 0 times R. That means the left side of the y-axis, minus infinity comma 0 times R. That region is open, and R times minus infinity comma 0. R times minus infinity comma 0. That's the region, open region below the x-axis. The union of this and this is the complement of this in R2. Because both of these things are open in R2, so their union is also open. So that's how A is closed. Next we have example 3. Here we consider the set R of real numbers but with the finite complement topology. Let's recall the definition of this topology also. It is that topology where a subset of real numbers is considered to be open if either its complement is finite or the subset itself is the empty set. Now, when do we have the complement of a set finite? Precisely when the set itself is the complement of a finite set. So that's why I have written like this. Since here open sets are the complements of finite sets along with the empty set itself. The complement of empty set is R, which is not finite, but because we need this in any topology, so that's why this is also there extra. And by our definition of closed sets, the closed sets in a topological space are precisely complements of open sets. So what are complements of this type of sets? Finite sets. So finite sets are closed in this topology along with the complement of this, which is R itself. That is also closed. Now before we see example 4, let's note something which you may have noticed in this example. Let x comma tau be a topological space. Now we already know that the set X and the empty set are both open. They belong to the topology. So by the definition of closed sets, their complements will be closed. The complement of X is the empty set and the complement of the empty set is X. So the empty set and X are always closed in every topological space. Just like here, R is closed. Example 4 next. Let X be any non-empty set with the discrete topology. You already know the definition of the discrete topology. That equals the power set of X. That means every set is open in this topology. And closed sets are complements of open sets, because every set is open, so every set is also closed, because every set is the complement of its complement, which is open. So that's why in the discrete topology every subset of X is closed. Next, example 5, where we consider the following subset Y of R, where R has the usual topology and Y has the subspace topology that it inherits from R. Y is the union of this closed interval 0, 1 and the open interval 2, 3. Now you note this. If you take the intersection of Y with this open interval minus 1 over 2, 3 over 2, then you get the closed interval 0, 1. So by the definition of subspace topology, this is open in Y. It's not open in R, but it is open in Y because it's the intersection of Y with an open set in R. And that is why by the definition of closed sets, the complement of this in Y, which is nothing but this, is closed in Y. It does not look like a closed set. I mean, closed means it should not always be closed interval. It has to follow the definition. So this 2, 3 as a subset of Y is closed in Y. Similarly, we have the open interval 2, 3 as the union of Y and itself. And this is open in R. So again, by the definition of subspace topology, this is also open in Y. And that is why its complement, which is this closed interval, is closed in Y. Next we have theorem 17.1. Let x, tau be a topological space, then the following hold. You recall the definition of topology. There you have three conditions which define open sets in a topological space. Similar properties are also satisfied by closed sets. Not exactly the same, but similar. The first of which is that the empty set and X are always closed in X. Actually, this is what we saw just now in that note. Number 2, any arbitrary intersection of closed sets in X is closed in X. You can compare this with the similar property for open sets, which actually is not a property. I mean, it's a part of the definition that an arbitrary union of open sets is open. Here, any arbitrary intersection of closed sets is closed. And then there is another one. And the third one is this. Any finite union of closed sets in X is closed in X. The corresponding thing that we have in the definition of a topology for open sets is that any finite intersection of open sets is open. Here we have finite union of closed sets and it's always closed in X. We will prove this in the next video. We have already seen how this is true in that note, but we will prove these two things and then we will see other things as well.